Okay, so greetings everyone. So we're still on chapter 3 or lesson 3, chemical reaction and stoichiometry, and we're already on determining formulas. Okay, so determining formulas. So the percentage composition of a compound leads directly to its empirical formula. So when you say empirical formula or simplest formula of a compound, it is the formula of a substance written with the smallest integer or whole number subscript. So for most ionic substances, the empirical formula is the formula of the compound. However, this is not often the case for the molecular substances. So as you may recall, the molecular formula tells you the precise number of atoms of different elements in a molecule of a substance, while empirical formula merely tells you the ratio of numbers of atoms in a compound. Okay, so let's have an example. So this one, we have determining the empirical formula from the masses of elements in a binary compound. Okay, so the problem is we have a compound of nitrogen and oxygen is analyzed, and a sample weighing 1.587 grams is found to contain 0.483 grams of nitrogen and 1.104 grams of oxygen. Now, the question is, what is the empirical formula of the compound? Okay, so basically, this compound has the formula of um, NXOY, wherein X and Y are the whole numbers that we need to determine. So it is also given here the masses of nitrogen and oxygen. And if we convert the masses of each of these elements to mole, they will be proportional to the subscript in the empirical formula. So the formula must be the smallest integer ratio of the element. And to obtain the smallest integers from the most, we divide each by the smallest one. And if the results are whole numbers, then they will be the subscript of the formula. Okay, so just like what we always do, or just like what we did in our previous examples, we first determine what is required. So for this one, we have ang gipangita nato is ang empirical formula of the compound. So next, we write what is given or we look for what is given. So as for this example, given nato ang masses of the nitrogen and the oxygen. So we have 0.483 grams of nitrogen and we have 1.104 grams of oxygen. So now, since we are given what is required and what is given, we can now solve for the mole of nitrogen and oxygen. Okay, so we are going to first determine the mole of nitrogen. So we first write the mass of the nitrogen. So we have 0.483 grams of nitrogen, and then we simply multiply it by its conversion factor. So we know that 1 mole of nitrogen is equal to 14.0 grams of nitrogen. So we simply cancel out the grams of nitrogen for us to be able to get our desired unit of which is mole of nitrogen. So we simply calculate 0.483 times 1 over 14, then we will be getting 0.0345 mole of nitrogen. So we do the same thing in calculating the mole of oxygen. So we first write what is given or the mass should first write the mass of the oxygen. We have 1.104 grams of oxygen times its conversion factor. We have 1 mole of oxygen over 16 grams of oxygen. Now, again, 16 grams of oxygen is from, since we know that the grams are the molecular mass of 1 mole of oxygen is equal to 16 grams of oxygen. Okay, so we simply cancel out the grams of oxygen and then we calculate by multiplying 1.104 times 1 over 16, and then we'll be having 0.069 mole of oxygen. Okay, so in order for us to obtain the smallest integer, we simply divide each mole number by the smallest one. So in this example, we have this one. We have 0.0345 mole of nitrogen. So in order for us to get its empirical formula, you have to simply divide it by 0.0345, and you also do the same thing here, 0.0345. So when you divide this or when you calculate this, you'll be having 1, and for this one, you'll be having 2. So we know now that the ratio of the number of nitrogen atoms to the number of oxygen atoms is 1 is to 2. We have 1 is to 2. So since we already now have the ratio, we can write this as in N, the empirical formula is N1O2. But since um, we have the subscript of 1 in the nitrogen, you can simply write NO2. Okay, so this is now the empirical formula of nitrogen oxide, dioxide. Okay. Okay, so let's now have another example. We have determining the empirical formula from percentage composition. So the problem is chromium forms compound of various colors. So sodium dichromate is the most important commercial chromium compound. And now, from which many other chromium compounds are manufactured. Okay, so it is a bright orange crystalline substance. And an analysis of sodium dichromate gives us the following mass percentages. So we have sodium is 17.5%. For chromium, we have 39.7%. And for oxygen, we have 42.8%. Now the question is, what is the empirical formula of this compound? Okay, so first, okay, so here we need to determine the whole values of x, y, z, just like what we did earlier. So we simply write NaX, kani siya kahit to show lang ha. So NaX, CRy, and OZ. So we first determine the values of x, y, z, and then we use the composition. We should use the percent composition of the data to determine the moles of sodium, chromium, and oxygen in the compound. And then we can use mole ratios of these elements to determine the empirical formula. So in this given problem, we also assume for the purposes of the calculation that you have 100% or we have 100 grams of substance, and then the mass of each element in the samples are equals the numerical value of the percentage. So for example, for sodium, since we are given 17.5%, so we also assume that 17.5% is now the mass of sodium. So we have 17.5 grams of sodium. Okay, so since we will be doing what we have been I know wrong. Okay, so we will okay, so we'll be doing just like what we did. So first you write what is required. You have empirical formula of the compound. And then you write what is given. You have 17.5% of sodium, you have 39.7% of chromium, and then you have 42.8% of oxygen. Okay, so since we now know what is given and what are required, we can now solve for the problem. So of the 100 gram percent of sodium dichromate, you have 17.5 grams is sodium, and then we have 39.7 grams is chromium, and then you have 42.8 grams is oxygen. So you convert these amounts into moles. So first we'll be determining the mole of sodium. So we use the mass of sodium given in this problem. You have 17.5 grams of sodium, and then you simply multiply by its conversion factor, and we know that 1 mole of sodium is equal to 23 grams of sodium. So you simply cancel out the grams of sodium, and then we'll be having our desired unit, which is mole of sodium. So you simply multiply 17.5 times 1 over 23, and then we will be getting 0.761 mole of sodium. So you do the same thing to chromium and oxygen. So we have here mole of chromium is equal to 39.7 grams of chromium times its conversion factor. We have 1 mole of chromium is equal to 52.0 grams of chromium. So you simply cancel out its grams, and then you calculate by multiplying 39.7 times 1 over 52, and then we will be having 0.763 mole of chromium. And for the mole of oxygen, you also write the mass of oxygen given in this problem. So you have 42.8 grams of oxygen times its conversion factor. You have 1 mole of oxygen is equal to 16.0 grams oxygen. So you simply cancel out the grams for us to be able to get the mole of oxygen. So you simply multiply 42.8 times 1 over 16, and then we will be having the product of 2.68 mole of oxygen. Okay, so now you divide all the mole numbers by the smallest one, just like what we did earlier. So this is for us to get the empirical formula. So for sodium, you simply, since ang pinakagamay ani is ang sodium, you have this one, 0.761 mole of sodium. So mo siya ang pinakagamay. So you divide all of this by 0.761. So for sodium, we have 0.761 mole over 0.761 moles, and then the answer is 1. For chromium, you have 0.761 mole over 0.761 mole, and then you also be getting 1. So remember, you first write ang imong answer diri the one you get in determining the mole, and then you divide it by um, the smallest answer, the smallest one. So you have 0.761. Okay, so for the last one, you have for oxygen, you have 2.68 mole divided by 0.761 mole. So you have 3.52. So now you must decide whether these numbers are integer within experimental error. So if you round the last digit, this one, you'll be having 3.5. So in this case, ang subscript nemo will not all be integers. So this one, it's illustrated this one. So dili siya tanan integer since you have 3.5. So in order for us na ma-integer siya, you simply multiply this by 2, and then imong 3.5, it will become 7. So it's now an integer. So imong empirical formula now is you have Na2 Cr2O7. So this is now your empirical formula. Okay, so let's move on. We have here molecular formula from empirical formula. So, so the molecular formula of a compound is the multiple of its empirical formula. So for example, the the molecular formula of acetylene, you have C2H2. However, it is also equivalent to CH times 2. This one. And another example is we have the molecular formula of benzene. We have C6H6. However, it is also equivalent to CH times 6. So therefore, the molecular mass is only the multiple of the empirical formula mass, so which is obtained by summing the atomic masses of the atoms in the empirical formula. Now I want you to remember for any molecular compound, you can simply write molecular mass is equal to N times the empirical formula mass, wherein N is the number of the empirical formula units in the molecule. You get the molecular formula by multiplying the subscript of the empirical formula by N, which you calculate from the equation, this one. So you have N is equal to the molecular mass divided by the empirical formula 1 mass. So once you determine the empirical formula of a compound, you can now calculate its empirical formula mass. So if you have an experimental determination of its molecular formula, you can now calculate the N and then the molecular formula. So let's have examples